Oh, you're muted, Leonard.
Yeah, all right. So I'm going to start with a short intro because I'm not 100% sure if I've met everybody. Very short. I'm Leonard. I'm one of Kristen's PhD students. I've been doing that for a few years. Have been working with the AERA system for a few years now. And lately I've been implementing parts of it in a different way, in a new way, where I used Elixir as a programming language to implement some of the parts of AERA that I found most interesting in a different way so that I can play around a bit more and get more ways of interacting with it that I needed in order to do my work. And this work is all revolving around planning for uncertainty in a non-axiomatic world, you know. This all started with the problem, a bit of the background of AERA and why this was a problem. AERA uses subsymbolic data or symbolic, it doesn't really matter, but also subsymbolic data to reason over and produce plans for interventions through backward chaining and forward chaining. So when a goal is injected, the models are being chained. Each model consists of a left-hand side, which is the cause of something, a right-hand side, which is the effect of that cause, and a set of arguments that kind of build the context in which this model, this causal relation holds. So during backward chaining, the system can analyze which kind of contexts it needs to it needs to change the world into in order to use causal relational models that then lead to effects that are desired in order to achieve the goal. Now, the problem if you go into subsymbolic reasoning, so direct sensor data without any pre-processing, without any symbolization or discretization, is that every sensor that you use is noisy and all data is always uncertain. You already get problems with just floating point arithmetics where exact matches do not work anymore. So what I wanted to do is to introduce a way to reason with sensor uncertainty, sensor noise. And this all came out to be a bit larger than I expected at the beginning. And my idea was, that this uncertainty that we have in sensors and in actuators is not something that necessarily should just be, as a plus minus range in which we discretize information, but rather something that we can use in order to plan how precise movement needs to be, how often the system needs to look at a particular variable in order to know whether it is within range or not. I'm not going to go too much into detail of that part because there's already a paper on that, and I presented that work in like 2 years ago or something. I want to use this TRIPS session more to talk about how I believe that reasoning can be done in a. Oh, I just saw that the footer is wrong. Just ignore the footer of the presentation. Sorry for that. More to see how can perception be used to guide commitment and recommitment of the system. How can perception be linked to the non-axiomatic reasoning? So how can we derive confidences of symbols maybe through the perceived sensor information that led to the instantiation of particular parts of the system in the first place. So what can we do with this uncertainty other than just using it as a pattern matching plus minus calculation, and instead use it to actually plan interventions and commit to solutions based on the information that is available. I also wanted to take a look at a different type of uncertainty. Sorry for jumping a bit. That is the uncertainty in plans. So a single task might have multiple solutions, and each solution is constrained by the environment actually acting the way that the system expected it to. So what happens if things go wrong? Right. So how to plan for eventualities even before they happened, and how to do this in a way that allows the assumption for insufficient knowledge and resources. I'm going to jump back a bit again. So parts of the motivating questions was how to link this uncertainty to non-axiomatic reasoning, how to include this uncertainty, and how to overcome the full computation of plans whenever any intervention is needed, but rather make it possible for the system to recommit to other solutions immediately when needed, when an eventuality happened that was not planned for in this particular branch of the solution tree. So the idea was to build a distributed reasoning system that uses, or that kind of is, a reasoning graph that computes solutions to tasks in a neighborhood computation. So instead of chaining a whole reasoning chain, which needs to happen once, of course, we need to do backward chaining in order to analyze what the goal is and what the initial state is. But instead of doing this multiple times, a tree is built, and this tree is dynamically adjusted and changed when necessary to new evidence that comes in. Perception feeds this tree from the downstream nodes upwards, and using uncertainty descriptions in sensor data, we can weight solutions on their success probability or their uncertainty, and use this then in order to commit which of the different solutions to choose from. So the decisions that can be done if you include this whole upstream information propagation of uncertainty descriptions now becomes less of a this model worked in the past kind of way, but more of a the environment is closer to this particular context right now in perception. So I assume that this particular solution that is based on this context is right now more suitable for the task. New evidence can then be integrated, so either contradicting or supporting evidence by adjusting these success probabilities, these certainties in a solution. And whenever one solution becomes more certain than a different one, the weights become higher, and the perception more confirms to a particular solution than to another. The system can recommit between different solutions without the need of any large reprocessing of the whole reasoning chain or anything, but rather just by changing one particular node of this reasoning graph, change the commitment from one branch to a different one. So in short, the idea was to have a system where each node in the graph, which corresponds to a model, to a assumption conclusion tuple, to a causal relation, each one of them competes for commitment by finding possible arguments, which is evidence in the environment, for or against it. This problem becomes a bit more clearer, I think, if we look at a very simple example, which is grabbing a sphere in this case, or grabbing a cube or something. Instead of having exact values of the gripper, so here you can see a gripper, here you can see the sphere. Instead of having exact values for their measurement where they are right now, we have distributions that describe the probability of the gripper being at a certain position and the sphere being at a certain position. Now, if we move the hand exactly over the sphere and open the gripper wide enough, we all can say, you know, grabbing will be successful. The sphere, even with this distribution, is within the gripper width, so grabbing, you know, will work. But what happens if we reduce the gripper width or move the hand just a tiny bit to one side? You know, given this distribution here, the success of grabbing the object is now fairly low. But how low? How precise? Do we need movement? Do we not need it? Should we maybe measure the sphere again? Should we look where it is? Or should we, you know, open the gripper so that we have a higher chance of actually grabbing the object? If we have singular values and exact deterministic values of each of those, this is not a real issue. You can move the hand to the particular position of the sphere, and then you know, if the gripper is wider than the sphere is wide, you know that you will be able to grab it. But once uncertainty comes in, we get a bit of an issue, especially if maybe the measurement of the sphere position is a whole chain of things that I have to do. Right, it might be that I can't just simply look at it, but rather have to do a whole bunch of tests in order to know where the sphere is. So I want to know how good my models are, how precise all my information is, how high my confidence is that the grabbing actually works. So for this particular example, the problem is, when is something grabbable, and under which conditions should the system commit to a movement of the hand rather than to a grabbing? A possible answer to that, or my idea here, is to use Bayesian statistics for this. So the confidence of grabbing success is derived from the sensor information of the sphere position and the hand position. So if we have the exact same setup, but now in red here you can see what would happen after the move command is executed by this delta value here, and depending on where the hand is, the probability that the grab is successful gets lower or higher if we move it closer, and the probability that the object is grabbable after the move command is executed changes as well. So now we can say, this one here is our confidence in the grab model, and this one here is our confidence in the move model. Of course, concerning the goal of grabbing the object. So the closer we go, at some point the grab probability raises over the move probability of success, and this gives us information when to recommit or when to change commitment between moving and grabbing, right? So. Yeah, this propagation of uncertainty that comes from the direct sensor information thus gives us a measure for the confidence that this particular solution to the task, which is either grabbing or moving, will be successful. Now, if we would do this through the whole graph, especially if we have a large task, a complicated task with a lot of causal relational models, this would very soon become computational and feasible. So how to do this under the assumption of insufficient knowledge and resources, especially insufficient resources? And what I have implemented here is, as I said earlier, this distributed partial reasoning. So instead of recomputing or propagating this information through the whole reasoning chain, it is only propagated as far as necessary. So there is one upstream node that decides between whether the objects are close enough already or whether we have to move first. And from there, the commitment happens, based on this particular node. And this one only feeds upstream the confidence in its plan. So in every single node along this plan, there can happen a recommitment whenever one of the branches of the tree becomes, gets a higher confidence in success than the other, without having the need to feed this information all the way upstream to the top level goals. Again, this means that these branches of the graph are trying to compete for commitment. And this competing for commitment happens through possible solutions that might increase the probability or the confidence in the plan. Upstream nodes then commit to downstream nodes. Downstream nodes update their upstream nodes. And all of this computation this way remains very, very localized in the branch of the reasoning chain that actually gets new information and evidences that matter, right? So we don't have to be concerned about any higher level goals while computing something more low level. I always use the example that, if you're walking somewhere and your foot moves on the pavement, there is no need to propagate this information about maybe a stone under your foot all the way up to some higher level reasoning instances if your leg can handle this eventuality by itself. So information is only propagated as far up as necessary, meaning as long as there is a possible solution that still has a high confidence, recommitment happens, and only if the contradictions happen that are unsolvable, it is being forwarded upwards in the reasoning graph to upstream nodes without otherwise burdening the upstream parents. I think this is pretty much a summary of what I already said. Recommitment happens through contradictions or to evidence that supports a particular context more than another one. And this way we can plan for eventualities even before they happen. So instead of building one particular a chain, one particular solution that we commit to, the system can build the whole different sets of solutions and keep them in memory alive, and commit to a particular one of them instead of having to choose one and then recompute any parts if this thing goes wrong. It's rather, an immediate change in commitment. Alternatives of these, of the same sub-goal are represented as branch of this tree, and switching between them then happens localized at one particular node. On the other hand, this is how this decision-making takes place and this commitment takes place, but where does this information feed into the system? That is through single nodes of this graph that are attached to the sensor information, that are bootstrapped through repeated observation at the beginning of the system's life cycle, where the distribution of the sensor data is being estimated right now in the implementation that I have through very rudimentary Gaussian noise estimation. And these perceptrons or these perception nodes can be adjusted by upstream nodes if they produce predictions of how the world will look in a later timestamp. They can send these predictions to the downstream perception nodes, and they can be tuned this way to, accumulate sensor data and not see, after I moved my hand, the hand is at a different position. This is first of all an outlier in the sensor stream of seeing the hand at the same position. But by tuning the perception nodes from upstream, we can build these expected values from predictions. If any sensor information is an outlier to the bootstrap distribution of the perception node, this can then be sent to learning algorithms, which, this is all an AERA implementation. I want to make this clear. This is not a new thing in the sense of a new architecture that I'm describing. It is just a way of implementing most of the AERA ideas that are already implemented in OpenAERA. And we can use the same, or I can use the same algorithms to identify novel situations, novel relations as already implemented in the OpenAERA system. That is the change pattern extractor that identifies unexpected changes in perception, and the prediction failure pattern extractor that checks whether a prediction actually comes true in a future timestamp, and if it doesn't, there's something that the causal relation model does not properly represent. And new models, when they are created, can be integrated in the reasoning graph. So I have a little example here, which plays together with grabbing of an object. We have this setup of a task. Maybe some of you already know this. This robot arm and a few cubes here, and the robot arm is tasked to grab this object. And the information that it gets is the hand position, the object position, and the width of the gripper. And from that, it's supposed to grab the object. It also gets a seed. Right now, it's the demo that I have prepared is without any learning. I'm just trying to show how this confidence propagation can happen if you include uncertainty in descriptions. So I'm going to open a little viewer here. And then I'm just gonna start this really quick. Okay. So you can see that the hand moves towards the cube. And the interesting part is here, this reasoning tree that has been built by the system. I'm not going to go too much into detail, but here, for example, we have one node that has different solutions available to it. This one here is the required context, that is the hand position. So in order to have something at the same position as the hand, which is necessary in order to grab it, we need to have a hand in the first place and the position of the hand. And then we have the possible solution of that the cube is at the same position, and the possible solution that the hand needs to move first before those two are at the same position. So this model computes the confidence that the cube and the hand are at the same position, including either factual information that comes through sensor information or predicted information that comes through a process that is, the movement of the arm. And if we look in here, this is a bit technical, but I'm going to show you anyway. We can see the state of this particular node. And in here, we can see this one here is the solution of moving first. This one here is the solution of those two being factually at the same position. This one here has a confidence of 0.0 because, as you can see, those two are at two very different positions. So the confidence that they actually are at the same position is really 0, whereas the probability or the confidence that a movement will lead to the two being at the same position is almost 0.5. So the commitment happens to, moving right now rather than assuming that factual information is correct. You can see this one here is a fact, this one here is a process that needs to happen. If we now move on, let me single step here. At some point, the system will do a recommitment. And now, I hate it with two screens. Now in this thing, now the factual information of them both being at the same position has a higher confidence than that movement will lead to them being at the same position. This comes from the uncertainty in the actuator. So whenever movement happens, without new evidence that gives us information about where the hand is afterwards, movement introduces uncertainty, whereas pure factual information does not, because this is only the sensor information that we already have. So in this particular case now, the movement is introducing more uncertainty than the single perception, and now the system grabs the object. And this recommitment happens on the fly without any need of computing higher level goals. So yeah, this is again this reasoning graph. And as I said before, this model of computing whether two things are at the same position is based on these three different nodes, and these nodes here compete for commitment either to factual information or to process execution. And as long as the result of the move model, which, as I said, includes the actuator and precision, has a higher probability of the hand of cube being at the same position later on, then the pure perceived data, the move model, is executed. And once this happens, this recommitment happens, the hand is close enough to the cube, the requirement for the grabbing becomes factual. This information is then streamed upstream to the parent node, and the parent node is then this grab requirement, which has this same position on its left-hand side, and the grab model can then be executed because it is provided with factual context rather than context that is predicted by downstream processes. This is a very, very simple demo, I know that, but just as a thought, the system could also have an own command for measuring the position of either the box or the hand. If that happens, we have 4 different confidences in the success of those two things being the sphere being grabbable or the cube being grabbable, and measuring hand now reduces the noise and perception. And if we go down with the noise, then at some point, if we go further down, here the hand, the system would commit to measuring the hand position, because it is very imprecise at the time, and we don't know whether the hand can grab the object as long as we don't know where exactly the hand is. And the more precise the hand position becomes, the higher the confidence that the object is actually grabbable, until at some point this confidence in grabbable raises over the confidence in that measuring the hand will lead to success, or measuring the box will lead to success. And then at that point, the system can commit between, the different things, between the different solutions. So if we start at a further over here, then of course it needs to move first, and then the closer it gets, it will get to a point where measuring becomes, a necessary thing in order to grab, because we don't know exactly where the hand is due to introduced noise of movement or imprecision of movement. And then once we measured the hand, the grab success confidence increases and the system can grab. So this would then be here more different branches from this node, each of them competing for commitment by forwarding information of the uncertainty in the sensor stream, and providing solutions by measuring or by moving the different parts of the environment. Yeah, so this is already it. I tried to keep it as short as possible because I thought, I'd love to get your thoughts and maybe a bit of a discussion of this started. So in concluding, I believe that using such a distributed reasoning, where parts, sub-goals are independent instances of the reasoning chain that each, stays alive in memory as a process rather than a singular computation of a chain, we can do a way quicker commitment and recommitment to different solutions based on the confidence in the success of said intervention. And all of this information upstream, whether to grab, whether to move, whether to measure, whether to do, even if we have later on nodes that need to be fulfilled, like this is only the beginning of a task where the cube needs to be placed somewhere else or anything like that. This is all derived all the way down from perception, rather than jumping in and having any sort of confidence measure that is primarily based on past experience. We can now also, I'm not saying that this is the only way to do this, or the singular dimension in which to measure confidence, but it is an additional dimension that gives us information based on the actual perceivable information in the world, and thus we can propagate information upwards. And the uncertainty in the plan, whether this will work or not, can be overcome by pre-computing possible alternatives. With pre-computing, I again mean that these nodes are being kept alive in memory, or if they haven't been used in a while, you can of course delete them. But generally speaking, these alternatives are already there. There is no need to do large computational effort when plans don't work out the way they were supposed to. Of course, we can't compute every plan that is possible. The system should rather try to, or we should implement it in such a way that the system goes a depth-first search rather than a breadth-first search, so that we have maybe 1, 2, 3 different solutions available to any task or any sub-goal. And these then, as I said, compete for commitment. So yeah, this all happens in a way through argumentation theory by, so what I haven't shown is the not statement. So if something forbids the instantiation of something else, this then just simply leads to a reduction of confidence in the solution, which then, from this emerges that there will not happen a commitment to this solution because the confidence of a different solution is higher. If there is no different solution, then the system will do the thing that it is, that it generally knows that it doesn't work. But I honestly have to say, personal opinion, that I would prefer a system that tries something rather than having a system, if it can't compute a plan, then it just does nothing. So my idea here was, rather, even if the success confidence is extremely low, the system could try to do it, because, maybe there is something that it didn't perceive yet, something that it doesn't know yet. Committing to an intervention is better than doing nothing if a task needs to be solved and there is not enough information available for the system to fully chain the whole plan. So yeah, that's, I believe, it from my side. Thank you very much for listening. I hope I didn't jump in too deeply, and that at least parts of it made sense. As I said, we have a bit of time now, I believe, and I would be happy for any questions and discussing this, because I think, I've been working on this for some time now.
Thank you. This was a very interesting presentation. I wonder, for the probability estimates, do you, for instance, in the case with the gripper, there is like this dependency, like, is the gripper already aligned with the object, and the probabilities, the change dependent on all these factors, and do, do, what gives the, how to say, is there like a model which relates these probabilities with each other, that is given beforehand, or can this also be learned somehow, how these probabilities relate with each other?
So right now I have implemented a few operators that are, for example, the similarity operators, so kind of the equals, the Boolean does it equal, or the adding of probability distributions to each other. That is the underlying operator semantics, right? So how can these distributions be changed by the system in the first place? In my current implementation, it can't learn that. It could, of course, learn a different model that uses these operators in order to transform the distribution differently. But just as previously we had a pattern matcher that matches the equal, does 5 equal 5. I implemented an operator that matches, that produces a confidence that two distributions are equal. Is that what you were asking for?
Yeah. Yes. This answer is good. Thank you.
Anything else, or did I manage?
So,
yeah.
Leonard, great work. I really like this. What does it look like for the system to like make a mistake in its selection of a course of action? Does it ever get into a state where it will commit to, say, try to pick up a cube when it's not possible for it to do that? Or does it perceive regularly enough that it realizes, like, as it's about to do it, that it can't, and so the error doesn't go farther than like starting to commit to it, but then it will retract? Like,
No,
I'd like to see an unhappy path of its
I can show you one. So if I start this and I do not provide it with all the information, so by the way, if you're wondering, I have a terminal here, it's just on a different screen, so that you're not annoyed by it. If I give it now as so little information that it cannot, like for example, if I leave out the gripper width, the system doesn't know, it could be that the gripper width is extremely large. There's no reasoning of whether two things are close enough to its distribution, so it can make a decision whether move or grabbing is more reliable. Then it will just simply grab. Right, because there's missing information, and as I said, if missing information is there, and the system can't chain all the way back to the necessary information, then it will commit to the highest confident solution. This can be a solution which has a confidence of almost zero or even zero, but it will commit to something.
Doing something, yeah.
If I then provide the information, it immediately chains and builds the correct outcome.
Yeah,
the
right.
Correct commitment.
In the first case, it had the expectation that after a grab it would be holding an object, but that failed. How does the system react to the failure of that expectation?
In the current state of what I'm showing here, it doesn't. I believe even if I would have it implemented in this version here, since the confidence that the grab would work was already zero, it is kind of a confirmation of that it doesn't work. Right. It's not like the confidence that grabbing works was very high and now all of a sudden it doesn't work. It is just that it was the only thing that the system could commit to, that it knew of. And therefore it committed to it, but with an extremely low confidence. And it was confirmed that this did not work.
So there wasn't a higher level goal that was driving it to try to do something, like the goal to be holding? No.
Oh yeah, that was the goal, to hold the cube, right?
Okay.
And there was one solution with the confidence of pretty much zero. That is, in the current state, just grab.
Okay.
Right. But as I said, with the confidence of almost zero. There's another solution that is move the hand within the gripper width. The hand such that the object is within the gripper width. But if it doesn't have the necessary information about gripper width, for example, or about hand position, there's no way for the system to commit to any sort of move command because, it's completely unbound yet. And therefore, this has a non-existent confidence. It's not a solution to the task because there is no solution to it. And therefore, the system commits to the only solution that it has, and that is grabbing.
Kind of generates babbling in a way.
That was a bit of my hope, that the system will execute commands that are available, even if they might not lead to a solution, especially in the beginning of the system, where there's very little information available. The system will execute commands nevertheless. Right, because it is the only thing that it knows, right? So, like the baby crying, it has a goal to be fed, but it only knows how to cry, so it will cry. Later on, after flailing around the arms, because this is also something that it can do, because crying maybe doesn't work right now, so the confidence is reduced, and so it starts to just throw around arms, and then this way it learns how movement happens, and then the more and more this grows, the more available solutions to the same problem exist with different levels of confidence to them. And then hopefully at some point there's one chain that actually binds and that actually produces a confidence higher than zero. And this is then, the thing that the system commits to.
I'll hold off questions because I have the privilege of being able to corner you at some point. So ask you my questions. I'll let others jump in.
I also, Tony, when you gave when you gave a little presentation the other day in the trip session with this, behaviors then lead to the system, like, for example, sensing something is just a behavior of moving your eye along certain axis along an object or something in order to build together your information structure. This really reminded me in parts of this by, as I said, this measuring, is also a way of the measuring of the box, for example, the box position, is a committable action, right? We could implement this in a way. And now, if you imagine a chain of these things where, at every single step, moving your eye from this corner to that corner, if you then see a corner, this produces a higher confidence in your models that it actually is a cube. You get this, confidence computation where perception immediately feeds through to confidence, is it a cube or not, by predicting if you move your eye over there, you will increase your confidence that it is a cube, then moving the eye, and then maybe you don't see a corner, but something completely unexpected. And this now immediately shoots down the confidence in measuring this object, whether it is a cube or not. So these, I hope that these behaviors can be emergent from building confidence models that are led by perception and predicted perception.
Yeah, I was interested to see that, actually. I mean, there's a lot of similarities in certainly at the high level that we're talking about, combining, your approach and my approach, that there is quite a lot of commonality there. Bits that at the moment I'm interested to see how you move forward with it. They're kind of the missing bits, really, in a sense, is that the basic learning that Patrick spoke about, where currently you're providing some of the pieces at the moment. And it would be really interesting to see how you're going to incorporate the temporal aspect and the learning of the very basic behaviors that then you can combine into these chains. So I guess really the next bit is the bit that I've been trying to solve for my problem, and you're working at the next level up, which is how you're combining those pieces into combining plans based on perceptual feedback.
Yeah, and that's also why I asked in your presentation whether you, went all the way down to the sensor information and uncertainty descriptions there, because it really reminded me very strongly of us working at a similar problem from two different angles.
Yeah, for sure.
And I have one last question, which is the granularity of action. Like, is it like that invoking a grab procedure, and that one is then handling the picking up of the object, or what is the granularity there? Does it like pass a parameter for like the color of the object, or?
No, right now in this demo, it's really so movement is done through the delta position of the hand, right? So I have an inverse kinematic of the robot arm running in the background. The system tells where the arm should move. Grabbing is a routine that is implemented in the Weebots engine. So there's just a grab command sent from the system to the Weebots environment, and then a routine does the actual grabbing. But especially since I've got it now so far that this gripper width and object width and all that kind of stuff plays together in making the decision to grab or to move, or I already have it implemented that, you know, hand rotation is being as a quaternion sent to the system. So going forward, I really hope that opening the gripper, closing the gripper to particular values, you know, moving the hand down so that it is directly above it, will be possible. I do not think that I will make it in any way to have the actual, you know, joints of the robot arm being controlled by the system, because this becomes extremely complex very, very quickly, and I don't think that I have time for that and nerves for it right now. But maybe at least the grabbing of the object, like the actual opening of the gripper to the value that is necessary in order to grab the object, right? Even if there is a bit of an the two are not perfectly aligned, and then closing the gripper so that the object is held is something that I really would love to see.
Makes sense. I could also imagine that some higher level operator arguments could make sense, like potentially in the easiest case just a position where the arm has to go, but also potentially like some discrete arguments, like how hard it should grab object or things like that.
Mm-hmm. Yeah, definitely. It's also, I think it would be very interesting to see, you know, if you either, like how hard to grab an object. If you have an egg, if you grab it too hard, you know, you will fail the task by just breaking the egg, or having a wall next to the cube so that you're not allowed to overshoot at all, right? So that you have to slow down before reaching the cube so that you're not hitting the wall or anything. That would also play very nicely together with the with this, you know, uncertainty of movement, which must then be reduced so far down that you can be certain that you're not hitting the wall, right? So the movement of the gripper, the uncertainty in how far you close it must be below a threshold. What happened? Must be below a threshold such that the egg doesn't crack, right?
Mm-hmm. That makes sense.
With the movement, I wanted to show you really quickly with this, you know, it's actually not just simply sending a singular command to move to the cube position in one single goal. It is constantly receiving new information, as you can see here, sending messages. So if I move this, you know, the arm will, or should at least. No, it's not. Okay. Huh. This worked yesterday. I tell you, it should follow. I was just about to say, yeah, that's demo once again. It really should follow. I don't know why it didn't, but yeah. Mm-hmm. I should have just left it out.
This was my next question actually, which is, yeah, how do you, if you were to put it into less of a static and more of a chaotic environment, like how would you expect it to fare? Or if you don't think it would fare well, like how would you iterate on it to equip it to handle things like, for example, its target moving either predictably or unpredictably?
Yeah, I really don't know why it isn't happening right now. Try again.
Move,
yeah, just
move
try
less.
again.
Move less.
I did some last minute quick fixes, I thought, just like an hour ago. So maybe that was one of them.
How does it know the position of the object to grab? Does it know from the simulation, or does it
Yeah,
through perception?
from the simulation.
Oh, uh-huh.
Nope.
No. Then this was my last minute quick fixes. Maybe I can even revert them, but I don't want to do that live now.
Demo.
But it's a bit less deterministic than the existing AERA architecture. So sometimes because I added some noise to the cube position and the hand position here in the Weebot simulation, it becomes a bit unpredicted, and sometimes it grabs the object wrong and then it re-grabs and tries to grab it again. But as I said, I don't see it right now, so I'm guessing.
Let me jump in and say something which you didn't mention. Maybe you thought it was too technical, but from what I understand, the reason you chose Elixir is because it's a real-time system where processes can receive messages and adapt their state, and that's what your system is doing. That's how it's going to be able to react to the movement of the object while it's running its system.
Yeah. So each of these.
That's why the choice of this particular programming environment.
Yeah. Each of these nodes in this graph is so Elixir runs in the Beam virtual machine in the background, and within this Beam VM, you can start processes which can send messages between each other. So this each of these nodes is an own process within the Beam VM that can take messages and send messages. So they are a bit in the sense like microservices or something, or ROS nodes or whatever you want to call them. So these processes can stay alive over a prolonged period of time. So even if this goal is achieved and the cube is grabbed, we can keep all of this alive, and when the next goal is introduced to grab something else, we can immediately, or the system can immediately chain through this existing network of nodes to find a solution that is already available. So it doesn't even have to plan again if a task that has already been done before is asked for again. Of course, this then runs very quickly, I believe, into memory issues. So you might not want to have this as a massive, gigantic graph where you never delete any nodes. So forgetting will be a crucial aspect of this. But new information, for example, that movement didn't work, or that a different solution to grabbing is made available, can be immediately integrated by actually connecting a new node to this goal of having an object in your hand, and then having new information structures from there. So there would be some sort of memory management that needs to happen in the background, as a future thought, future thought, where these nodes are being, chained and rechained and reconnected. I have one implementation where there is no beginning. Everything is just a mesh of nodes that communicate to each other. I tried that; it didn't work really well, at least not on the first try. So, since I have like a dissertation to write and everything, I didn't follow this branch too much. But I see this more of a growing network of models where the system is its own knowledge base, right? So right now I have these models here from where the system can draw in order to do backward chaining. But generally speaking, each model that fits, the left-hand side and right-hand side fit together, you can just create these links and have them stay alive in the system, in the memory, as a communication chain where information can be passed. So there's no need of chaining when when information or when a goal is introduced, but rather some sort of existing architecture, existing node configuration that produces a solution with the confidence that is high enough, or with some sort of confidence, and then the system commits to the one with the highest confidence, right? So this is not thought as produced for every single task on the fly once and then redoing everything, but rather as a standing graph that is extended over time. And you can with Elixir, that was another thing why I committed to using Elixir. Each and every one of those nodes can be easily run on different machines, on different parts of a distributed system. So this is all handled in the background with a Beam VM. I could start this now on a different machine with a one-liner, or I could start this particular node on a different machine with a one-liner, and this really helps. And if this works, that this thing can grow over time, then at some point you really have to think about distributing the architecture over or the system over multiple machines, probably. But that's, as I said, future music. That's nothing that I'm concerned with right now. But when you have to decide on a programming language to use, you might want to take into consideration where this might go in the future.
Nice, thank you.
Okay, I have a few questions. First,
yes, please.
Very, very interesting presentation. I think the core idea problem we can say is about when to take action with uncertainty. I have several questions. I want to start from the lowest level. That is about measurement of uncertainty. I think, well, at least if you allow me to use the vocabulary we use in NARS. I think in this discussion, at least there are three types of uncertainty involved. It should be more clearly distinguished. One is confidence, which you have talked about. Another one is what we call frequency, and the combination of the two we call expectation. For example, in your previous description, you said when you just simply, you don't know what to do, you just directly close your grabber, the confidence will be low. But in my terminology, no, actually it's the opposite. The confidence will be very high because that's not going to work, okay? So the frequency will be very low because the success rate will be close to zero. Confidence is very high because I have tried that many times in the past, and it never works. Or you can say the expectation is low because expectation is the two combined together.
Totally agree with you.
Yeah, I think that's also related to some of the other comments. For example, when you say you pick, when you have several plans, you pick the one with the highest confidence. Actually, no, at least that's not the case in NARS. You pick the highest one with the highest expectation. Again, according to the previous example, confidence low, confidence high, actually may correspond to a situation where it doesn't work. You still have a high confidence. It's just because it's kind of like to the negative side. So, which I actually agree with what you said before. You see, if you don't have a good plan, you still want to give it a try. Okay. In that case, you may know, for example, when you're solving a very difficult problem, and there are several options proposed. All of them actually have a lot of negative evidence, not much positive evidence. But you still have to pick one, which in that situation, what you compare with each other is you use the expectation level. It's kind of like relatively lower negative evidence, even if there's no much. It's kind of like, when we're doing AGI at the beginning, no one really knows. It just, you pick the path, it looks more likely because you have less negative evidence compared to the other paths.
Can I jump in?
Sure.
So the frequency, if something has a lower frequency, it's because alternatives happened. And I think Leonard is handling that, but by this, it wasn't clear in the screenshots, but the alternatives are represented, and they compete. And this idea of competition between alternative counterfactuals is explicitly represented in Leonard's system, whereas in NARS, it would just, if there were other things that happened in the past, it would just result in a lower number of frequency. There wouldn't be an explicit representation of the explanation for why another thing happened. So I think the frequency is explicitly represented by the alternative branches that are competing.
Well, I see your point. But still, I think it's better to have, alternative play a major role. Okay, even if you have a very high frequency, if another guy have an even higher one, you will still use the other one, right? You don't shoot. So the problem here is not we're not talking about how high a frequency is high enough for you to make a commitment. There is no such thing. It all depends on who else you compare with. Okay, so in that aspect, I fully agree with you that the existing other commitment or alternative make a major role in your choice. But that, at least in my terminology, that is the consideration of the choice rule. The choice rule will pick the most promising one among the candidates or among the competitors. But in terms of the measurement itself, frequency is basically just the success rate. Okay, whether there are other guys, it doesn't matter. What matters is the high success rate. It doesn't guarantee you to be picked by the final commitment. So that's one thing. Another thing, confidence. Well, if we're using NARS terminology, is basically how much you have tried. Which is related to the previous discussion. Also, Leonard made the comment, which I agree, that is, it's kind of like a balance of your current input information or your immediate sensation compared to your past experience. In this experiment, I think the past experience haven't played a major role yet, which will be introduced in according to Leonard, which I agree, okay. But that one will gradually actually contribute more to the confidence level because, something, even I haven't tried in this scenario, I tried in other scenarios. So I'm confident about that plan, okay. But now if we don't have past experience to talk about, confidence also make a major contribution, especially about what Leonard mentioned before at the beginning about that concrete example. Say if you want to grab something, there are two conditions, at least in this experiment. One is the movement, one is the grabber need to be opened wide enough. Okay, and also it need to be in the right position. Of course, both of them will have some tolerance to uncertainty. You cannot be perfectly there, and whether it's open wide enough is uncertain. But logically speaking, you can say each of them is uncertain. Then you take the conjunction of the two because you need to satisfy both conditions for the grabbing to become successful. So in this case, the final conclusions, confidence will depend on your confidence on each of the two by itself. Okay, whether it can be calculated by the Bayesian approach, that to me that's a separate story.
I want to add. So these models all also have their own confidence values, right? So, for example, the move model, it gets information from downstream through perception, and then it multiplies it with a value between 0 and 1, right?
Yes.
Which is the confidence in them. This is, I didn't mention it because I didn't want to go too much into detail, but yeah, this is, you know, if you have two different models and one was very, I have tried often and I'm very confident in that it works, and then I have different one which I have very little experience with, but one of them produces a very high frequency, then it is multiplied with the confidence in the model itself, right?
Yes.
So it is adjusted to the confidence in the model itself. Yes.
Yes, here I completely agree, because confidence will sometimes you use other words, say reliability or accuracy. All of those are related to confidence, which I fully agree. And so that's the second point. That is, confidence may come from several sources. One is past experience. Another one is the quality of your measurement itself. But by itself, confidence does not mean whether you're successful or not. That's a frequency. Okay, confidence can be negative. You can be negatively confident about something does not work. So I think that's a major point I want to make.
Okay. Yeah, thank you.
Finally, it's a big one. I think that's actually the biggest difference between how this kind of thing will be handled in ours. We don't have it yet, but compared to what we have, for example, what Patrick have done, I think the major difference, conceptual design, is in the use of this reasoning graph, which also you mentioned, you know, forward chaining, backward chaining, and how much you want to propagate the calculation and so on. They all come from this use of this planning graph, which we don't have in ours. Which also I think is related to Jeff's previous comment. That is, we don't clearly have a direct representation of alternatives and competition and so on. Instead, kind of like each action is evaluated by itself. It's what we call schema recently, just with precondition and consequence and action, instead of chaining this whole thing together. You may notice that in my previous discussion, I always use forward and backward reasoning. I never use forward and backward chaining. The reason is kind of like not chained together as a graph. I can see the benefit of that. Actually, we have something kind of like a half graph, because this forward and backward process is actually, you always start from a backward reasoning process. Usually, from the goal you want to reach, you want to kind of like divide it into smaller pieces. Then you do forward. You take your action, you calculate it, and you actually get the result. So this graph is always kind of like traveled twice. First, you go backwards, then you go forward. If you have a complete graph already developed, then the forward process will have something to depend on. You know where you want to go because you know the backward process already built that graph for you. The problem about it is you already mentioned the maintenance itself can be very expensive, especially when we're talking about you have multiple tasks, a task come and go. You're not repeatedly always do the same thing again and again. So when to keep such a graph and for how long you want to propagate each of the calculation, all of them will be an issue. But on our side, the problem is if you cut it into pieces, you only keep the pieces. Then if you need to use the same thing again and again and again, it will become inefficient compared to, you know, you have a graph already there, so you can depend on it. I think the compromise in ours, it will depend on the use of compound term. So if I do some chain reaction again and again, if I always do, you know, operation number 1, operation number 5, operation number 7, instead of keep a graph, I just bundle them together into a compound operation. I will just call it operation K so that I know that whenever I do that, they will be further divided into those 3 steps. I think clearly each of this approach have its advantage and weakness. To a large extent, again, I go back to your assumption of your working environment. How repeatable will the procedure will need to be in the future, or how many different types of tasks you want to deal with. I think that's the key.
Yeah, it's something that we have discussed before as well, is this idea of compiling down parts of the reasoning chain that fit together and that is repeatedly executed into a single executable thing, right? So I'm just going to pass this over to operation K, and that will do 157, right? I think that this is reasonable in a lot of cases, but I nevertheless think that it is a bit oversimplifying, to be honest. Because if I introspect myself, there's this thing that I do over and over again, which is moving my leg in a way that I, walk. I do this unconsciously and I don't have to think about it. So there is an argument for this is just a subroutine that is passed to a different part of my system that is executed. But if something goes wrong, I can immediately and directly intervene on this issue of something going wrong, right? If I walk down some stairs and this feeling of missing the last step that we all probably had in our lives is something that is very, very immediate, and I can immediately also counteract the what is following from that. So I felt like compiling it down or compounding it into single operation instances partially at least removes this immediate intervention on operation number 5, right? If I execute K instead of 157, am I not losing information there? Or is it just for the reasoning chain, for the reasoning process itself, that it uses K instead of 157?
Actually, you can have both. What I mean, I completely agree with the point you make. Okay, the point is when you combine a sequence of operations into one, you are not losing the original one. You are not losing the possibility of using each of them one by one. Like the examples you said, for a lot of daily routines, we just use our habit, and then when it fails. It's only when it fails, we go back to the original. We say, okay, it must be, after 1 and 5, instead of do 7, now I need to do 9 because the situation is different. But you don't do this kind of planning every time. You depend on your routine, wherever they work. But the trick part is, of course, you never really know in what situation it works or not. So you build a lot of them. You let most of them die. Lose in the computation just because it will be high with a high failure rate and so on, and or it become irrelevant. You are going to forget them. What my point is to make them, to me, is absolutely necessary, but you cannot completely count on them, and especially when you make such a routine. You don't really know whether it will be useful or not in the future. You cannot make that decision at that time. You have some clue, so you can give it some kind of priority or whatever you call it. But you will like the time, the future time, to decide which one will survive. But even if there is a high rate of failure, do not do that and always depend on planning from the basic operation. To me, that's in the long run is not a good idea. This directly comes from, as you said, from psychology. That's what we call skill acquisition, right?
I think there's more overlap than we might think. When we look at a graph like Leonard shows, or when I show these argument graphs, um, you know how trace route works on the internet, right? The internet is a bunch of nodes, and there's a communication protocol, and that's really what's important. Is a node can send out a message, but only some particular nodes will pick up the message and do something with it. And so the internet doesn't, when I send a message from my house to your house, it doesn't really maintain a graph. It just has, one can produce the graph for us, for when we want to be engineers and we want to debug it. Then we run traceroute and produce a graph of the connectivity among all the nodes. But the internet doesn't explicitly have a graph. It just has a bunch of individual nodes with their own communication protocols. And we impose this on it just so we can reason about it.
Yeah, I think I agree with this comment. There is some gray area in between. It's kind of like, yeah, you have some basic elements, which is your foundation. You always need to depend on them. And on that foundation, you build some intermediate structure. The problem is, because of the changing of the situation, you never know which structure will become useful or successful. So to build them is necessary. So in that sense, I kind of like understand the need for this kind of planning graph or reasoning graph. But on the other hand, we need to be careful, do not make too strong commitment about something we built so far just because it works in the past experience, in the past cases. Because if you're facing new situation, then they will actually cause more trouble than you don't have them, because you're going to be kind of too much biased by your past experience or your old habit.
I think we agree. I mean, Leonard, correct me if I'm wrong, but if you were to delete the right-hand side of the screen, your system could recompute it. It could re-arrive at this graph.
Sure.
Of course. Of course.
Sure.
And so the graph itself is not the knowledge representation. It's the communication protocol in between individual nodes and the kind of other nodes they'll match.
I will say it's a little bit more than that. It's kind of like it's the derived part of knowledge representation, because you still depend on it to guide your future actions, right?
Yeah.
But just to make something clear, this graph doesn't exist, right? This is just Elixir inheritance of process nodes. So this node started this one, right, in the background, but this node lives independent of that one. Right,
yeah,
so
it's a history of process steps
of how this was produced, this graph. But if I would remove this ancestry between those nodes, which is something that comes more from the Elixir programming language than what I'm doing here, this would just be a list of things just plain down. Right, it's just the communication happens through parts of this. So this one communicates with this one and this one, right? But this one also communicates with this one, but through these neighbors, right? For particular information stuff that goes through there. So the graph is more similar to what Jeff said. These are different nodes that have communication pipelines to other nodes, right, where they can send information to and from, get the information from. It's not in any way like a mathematical graph where I have actual edges, right? Just
or a semantic network, or like in traditional AI, it's not like that. Yeah.
Yeah, it's not permanent. I fully understand that part. I just say that whether it will have an influence to your future, not only as a record of your past. If as soon as it have some influence to your future decision making, then you will need to think about whether it will be more efficient to keep it, or it may cause some bias about your decision.
I'm pretty sure it will cause bias. the way I'm doing it here. I'm pretty sure of that, but this is also, in my opinion, something that comes from experience-based AI, right? If this is my experience how to grab stuff, and now I get the objective to grab something, then I will first and foremost rely on this, right? I'm not gonna start thinking about all the possibilities. How could I grab this object now? If I already have a solution available that is, on the forefront, I'm just gonna grab it. But yeah, it will introduce bias, definitely. It will introduce bias towards things that have been experienced before.
I completely agree. Actually, bias is not necessarily a bad thing. To me, bias and habit and efficiency, they're more or less the same stuff, right? You just need to be careful, and you need to know the limitation about it. That's all. That's all I want to say.
Yeah, thank you very much. Right, it's 4:30 on my side. I don't know, any other questions, or should we end the session?
I guess we can end it if there is no further question. Thanks a lot. This was really insightful and a lot of new ideas which you presented there. Very interesting.
Yeah, thanks everybody for the nice discussion and having me here. I enjoyed it.
Thank you. Then I will stop the recording.